Hi students, welcome to the next topic from moving charges and magnetism, and which is called moving coil galvanometer. Okay, have you seen galvanometer? At least practically there is less chance, at least in the school labs, and at least in some images you might have seen this one. But let's see what it is and why we are studying this topic here, and what is the importance of moving coil galvanometer. So write out the first heading, moving coil galvanometer. Moving coil galvanometer. Galvanometer. In this whole chapter, in short, I am writing this as MCG, moving coil galvanometer. Okay. Galvanometer in general, it's a generic device which is used to measure voltage, current and resistance. Okay, so first we will write galvanometer. First point, galvanometer is a device used to measure current, voltage and resistance. Current in general, there are multiple use cases will be there, but in general, galvanometer is a device used to measure current, voltage and resistance. What is mean by moving coil? A coil which can move. Correct, a coil which can move. So moving coil galvanometer. So we know galvanometer means it's a device which is used to measure voltage, current and resistance. If the galvanometer is used to measure voltage, then it is called voltmeter. If it is used to measure current, then it is called ammeter. If it is used to measure resistance, then it's called ohmmeter. But why galvanometer preceded by a term called moving coil? A coil which can move. So how it is connected with galvanometer? Galvanometer basic principle is, that is the heart of, we know the heart of the computer is CPU, central processing unit. Similarly, the heart of the galvanometer is moving coil. Okay, I'll tell you in detail the constructions and the working of moving coil galvanometer. First of all, what is the basic principles involved in the moving coil galvanometer? So the working principle, the next point is working principle. So the working principle of moving coil galvanometer is torque experienced by, last sessions we have seen, right? Torque experienced by a current carrying coil, torque experienced by a current carrying coil placed in a uniform magnetic field, In case of a uniform magnetic field, only torque. In case of a non-uniform magnetic field, both the torque and force will be there. So just we will write an additional point. In case for a uniform magnetic field, in uniform magnetic field, I can say torque not equal to 0, force equal to 0. Second one, in non-uniform magnetic field, torque not equal to 0, force not equal to 0. Force equal to 0 means all the forces will be getting cancelled, and the why torque is not equal to 0? Because the line of action is different. Last sessions we have different, right? Total force may not, the direction of torque is opposite, but not in the same line of action, in opposite line, so that one is in up and another is in down, so that it will undergo a turning effects. So remember this. So torque experienced by a current carrying coil placed in a uniform magnetic field is the working principle of galvanometer. We'll see how these galvanometers are working and what are all the terms are associated with this galvanometers. Okay, so let's move to the construction of galvanometer. So we need some space over here. We have to draw some diagrams. Okay, we'll see how it is measuring and how it is happening and how it is using. Okay, so you can write the heading called construction of galvanometer. Construction of MCG, construction of moving coil galvanometer. Okay, so the moving coil galvanometer is connected with, what is the main heart of this one, moving coil galvanometer? The main heart of moving coil galvanometer is a coil. So this is connected with a coil like this. This is like a spiral binding kind of structure. So it's going out and this is connected. These two I call it as terminal. Terminal means here I will give voltage or current, whatever I would like to use to measure the system. And here I have a magnet is placed, and here also I have a magnet placed, and this is the north pole and this is the south pole. The magnetic lines of force, north pole, south pole, north to south outside, inside south to north, remember this one. Magnetic field lines, this is called the magnetic field lines. So magnetic field lines, north to south outside and south to north inside. So this is the direction of magnetic moment, right? Well, last class we have discussed. Okay, so there is a lines of force will be here from north to south direction. So this is the magnetic lines of force from south to north. So now what happens? Now one thing is like here, this is connected with a coil and this is fixed over here. This is fixed over here. It's like a pivot, we'll say pivot, fixed. It can rotate. Okay, now what happened means I will tell you, this is a coil having n turns, this is simply a wire, nothing else. This is simply a wire. This, you know, north and south is a magnet. Okay, so this is a magnet, this is also a magnet, north and south pole. Monopole does not exist, right? For a magnet, both poles should be there, then only these things will be applicable. So let's see what all the things will be here. This is a terminal. So in the terminal area I would apply voltage or I will apply current. In this terminal area I will apply voltage or current. So if I am applying some plus volt and minus volt will be here, current will flow. When current will flow, what will happen? This is a current carrying coil is placed in a uniform magnetic field. So what will happen? The coil will experiences a torque, coil will undergo rotation. That is what we discussed in the last class. There we have discussed only one coil. Here we have multiple coils. Coils are there. So if multiple coils are placed in a uniform magnetic field, it will experiences a torque and this will get rotated. So of course, once this is rotated means this is inside the galvanometer. Galvanometer you have seen in your school. You might have seen in your school. What is galvanometer? Is like it's a black dappa you have seen in your school labs, right? Say. So that dappa. So outside this coil is connected with a needle and the needle will be getting rotating. So whenever a current is passed through the coil will get twisted. When the coil is getting twisted, the deflection needle will go to right. But what will happen? There is a spring will be here. This spring will give a something called, so whenever you stop the current, what you want? You want the coil to be bring back. So to take it back to the original position, the spring will give an opposite action. So the spring will give something called a counter torque. Torque in opposite ആയിട്ട് വരുന്നത്. This is called counter torque. ഇപ്പോൾ കറണ്ട് പോകുമ്പോൾ what will happen means when a current is passing through the coil, coil will rotate. Coil is connected with a needle, so needle will go to right. So whenever a current stops, what happen? I need to take the coil back. If the coil is rotating in opposite direction means this needle will come back to the original position. So who will take the coil back to the normal position? The spring will take to the back to the normal position. So the springs will give counter torque. So we will write one point will be there. Spring gives counter torque. Spring gives counter torque. Okay, so understand. So we'll just summarize the points whatever we have learned. The first point, when current passes through the coil, from where? From terminal. When the current passes through the coil from terminal, coil rotates due to torque in magnetic field. So due to the torque effects in a uniform magnetic field, coil will rotate. So the connected meter reading, the connected meter needle also rotate, and this needle gives the measurement of current. This needle in the meter scale, this is connected with the meter scale. So this needle, so this is connected, this is an inside structure. Outside this coil is connected with a needle will be here, and there is a meter scale will be here. Okay, so there is a meter scale will be here, something like this one. So this is connected with a needle, so the needle will be getting rotating. So this is connected with a meter scale like this. This you can draw. This is outside the box. This is what we can see, but this is inside the box. Okay, so this needle in the meter scale gives the value of if I am measuring value of voltage, current or resistance, whatever I am measuring, that value this needles will be giving. Okay, so the second one, and to take the coil back to the normal position. I want to take the coil back to the normal position. To take the coil back to the normal position, a counter torque is required. A counter torque. Counter means opposite. A counter torque is needed. Okay, to take the coil back to the normal position, a counter torque is needed. So who will give the counter torque? Spring will give the counter torque. Okay, a counter torque is needed. Balance I am writing will be here. The spring gives the counter torque. The spring gives the counter torque. The spring gives the counter torque. So that's all. Over. The spring gives the counter torque. Okay. So torque, the value of torque will be depends upon how many angle it is rotated. So I told this spring will be give a counter torque. Suppose the coil will be rotated by 1 degree. Correspondingly, if the coil is rotated by 1 degree means very small it is rotated, then this spring will give a small rotations, a small torque. So torque will give, so I will write next point, counter torque. Counter torque is directly proportional to phi. Phi is the angle of rotation. Phi is the angle of rotation. So counter torque tau equal to, proportionality sign is replaced with a constant C phi. So torque is equal to C phi, where C is called a constant. That's all. Where C is called the constant. Okay, so now I told coil will undergo a rotational motion. If the coil is undergoing a rotational motion because of the torque experienced by the current carrying coil placed in a uniform magnetic field. So when the current carrying coil is placed in a uniform magnetic field, the coil will give a torque, and this is the torque given by whom? So this is a torque given by whom? Spring. That's what it is called, counter torque. Okay, so torque from the coil will give a torque. What is the torque equation? M cross B. We know it is called M cross B, MB sin theta. M is called what? Current into area. So torque is equal to current into area into B into sin theta. This is for one turn of the coil, but here how many turns? N turns. So we'll multiply it with capital N. Capital N is the number of turns of the coil. So we know this is the torque from the coil. So this is equation number 1 and this is equation number 2. So the coil will be going in forward direction. Spring will turn it back to the normal position. So both the torques amounts are equal. So in that cases, what we will do? If both torque amounts are equal, what we will do? Torque is equal to C phi. Torque is equal to NIAB sin theta. We can equate these two, right? So these two equations we are going to equate equation number 1 with equations number 2. Both equations we are going to equate. So let's say C phi equal to torque NIAB. So I am equating C phi is equal to NIAB sin theta. So this is important. This is what is actually within the galvanometer. So both the torques will be getting equal. Okay. Next, we are going to derive certain parameters related to the moving coil galvanometer. Okay, couple of parameters will be there. We'll see what all that is. So this is important relations in case of a moving coil galvanometer. So let's go to the first term, and the first term associated with the galvanometer, the first term is called current sensitivity. Current sensitivity. For simply I am writing at IS. Different books are using different notation, but I am using IS. This is very easy. Current means IA, sensitivity means S. So current sensitivity is equal to the amount of deflection divided by current. The amount of deflection. Amount of deflection means what? Phi. Amount of deflection divided by current. I means capital letter I. So let's substitute these equations. Here I need phi by I in these equations. So which means phi divided by I. What is phi by I in that equations? Phi divided by I. N A B sin theta whole divided by C, the constant. N A B phi by I. This I is taken to this side. N A B sin theta by C phi. This is called the value called current sensitivity. Important. So this is called the current sensitivity, NAB sin theta divided by this one. Theta is the angle between the magnetic field and that of area vector. And the second parameter is related to this one, is called voltage sensitivity. Voltage sensitivity. We are representing this as called Vs. So voltage sensitivity means what? How we'll get voltage? Voltage sensitivity means deflections by voltage. So Vs equal to the amount of deflections. We'll say the amount of deflection divided by the amount of deflections divided by voltage. Voltage means the voltage in which I am applying across the terminals. Okay, so let's go ahead. I'll keep this equation for some time to have a reference. Okay, so fine. Next, so voltage. So Vs will be equal to 5 divided by voltage. How to get voltage? Voltage equal to current into resistance. Voltage equal to current into resistance. So voltage is equal to current into resistance. What is current from here in this equation, sir? C, let me put it as IR so that you will not confuse. What is I? I will be equal to C5 whole divided by NAB sine theta into resistance. This is called voltage. Now we'll go to voltage sensitivity. 5 divided by V is equal to 5 divided by V means we'll substitute C5R divided by NAB sine theta. So 5 cancels. You will get NAB sine theta divided by CR. This is called voltage sensitivity. So we'll write these equations in next steps and we'll put it in a box so that will not be get missed. So voltage sensitivity is equal to NAB sine theta divided by RC. C is a constant. C is not capacitance. Okay. Because C we are learning. Do not remember. C is a constant. I am writing C is a constant. C equal to a constant. Okay. Right. Not a capacitance. In a bad thought moment, this will come to mind like capacitance. No, it's not capacitance. It is a constant. Okay, so I have voltage sensitivity equations. I have current sensitivity equation. Hope that all these equations also there in your notebook. So please pause the video and complete it in case if you have not written. Okay, so I am clearing the board for all these equations. And I need one more equations, the last one. So voltage sensitivity is over, current sensitivity is over. I need to derive one equation, that is something called resistance of the galvanometer. Okay, resistance of the galvanometer. So write on the heading called resistance of the galvanometer. Resistance of the galvanometer. Resistance of the galvanometer in bracket RG. Okay. How to find resistance? Resistance of galvanometer is equal to, can you derive resistance equation from these two? Current sensitivity by voltage sensitivity is called resistance equations. So let's substitute will be here. What is current sensitivity? NAB sine theta divided by C. Voltage sensitivity NAB sine theta divided by RC. NAB cancel NAB, 1 by C, 1 by C. 1 by R will go to numerator, become R. That's what this is very important. The third one. Resistance of the galvanometer RG equal to current sensitivity. V is equal to IR equation 3. But no, current sensitivity is not equal to current. Voltage sensitivity is not equal to voltage. So V is equal to IR. So resistance of the galvanometer is equal to voltage by current. Voltage sensitivity by current sensitivity gone. -1. -1 mark in the Neet examination. Okay. So resistance of galvanometer is equal to current sensitivity by voltage sensitivity. Very important for JEE examination also. Voltage sensitivity based questions are there, as well as for a JEE paper. In some cases I have seen for IIT JEE main examination, even for JEE advanced examination also there are questions will be based on the concept. But in general for all entrance examination this is quite important to know. Okay, fine, perfect. So moving coil galvanometer basic theory, basic understandings are over. So let's move to the next major topic, which is related with this moving coil galvanometer. So next we are going to see the main two applications of moving coil galvanometer, which means how or in what way like the moving coil galvanometer can be make use of, so that we can use it to measure voltage and current and resistances. So in your syllabus we have only two things will be there: how you can use the moving coil galvanometer to use it to measure voltage, which is called voltmeter; how you can use moving coil galvanometer use it to measure current, which is called ammeter. So we'll go into one by one topic. So the first one, moving coil galvanometer, MCG as a voltmeter. MCG as a voltmeter, moving coil galvanometer as a voltmeter. Okay, so the moving coil galvanometer is there, galvanometer, and the resistance of the galvanometer is called Rg, and the resistance is normally very less, current sensitivity divided by voltage sensitivity, that is very less. Okay, so to measure voltage, a large amount of voltage, voltage equal to current into resistance. If I passed through a current over this circuit, say this current is called I. If I passed this current through the current, so the resistance, I cannot pass a huge amount of current, because galvanometer is a very sensitive. Sensitivity means what? Current sensitivity means what? Current sensitivity means for 1 unit of current, how much is the deflection? Phi divided by current is called current sensitivity, phi by Ia, which means for 1 unit of current, 1 unit means any unit, 1 milliampere edukam, 1 microampere edukam, 1 ampere edukam, in 1 unit of current, how many degree the coil will rotate, that is called sensitivity. Voltage sensitivity, for 1 volt how much degree the coil will rotate, that is called voltage sensitivity. We'll say sensitive. Sensitive means I am saying like I am very sensitive to the cold climate, which means that what? If a cold climate is appearing, I am very sensitive means my body will changes to the cold, hence I got some diseases. I am very sensitive to cold climate means whenever a variation in the cold climate is happening, I got disease. I am not very sensitive to warm climate, which means whenever a hot seasons will be there is a change in the hot seasons, nothing will happen to me, my body is stable for that. So whenever a cold climate appears, I have some changes will be there, because my sensitivity is very less. Within our friend circle also will say, hey, that guy is very sensitive, don't speak to them. We'll say like that, right? So if you say something in a little bit harsh way, he'll be get hearted and he'll feel very sad and he will start to cry. So sensitivity means what is the minor things you can give to somebody else so that he will start to react on that. That is called sensitivity. So current sensitivity means minor current you give so that you will see deflections. How much angle of deflection? You give a minor voltage and so you see the deflection. That is called voltage sensitivity, current sensitivity, etc. So to convert moving coil galvanometer into a voltmeter, a high resistance needs to be connected in series. RS. This should have a high value. Then only if you are measuring voltage across the device, you will get maximum voltage. Maximum voltage means the voltage across the galvanometer is equal to the current into resistance of the galvanometer plus the series resistance. So this is important. Remember this equation. They will ask you to find out the value of RS. So to convert moving coil galvanometer into voltmeter, what we need to do? We need to connect a high resistance in series. So write down the setting. To convert moving coil galvanometer into voltmeter, a high value of series resistance, RS needs to be connected in series. To convert MCG into voltmeter, a high value of series resistance needs to be connected in what fashion? Needs to be connected in series. Important. We will do some questions during our question discussion sessions, and yeah, based upon that we will get some throughput on that one. The next heading, MCG as ammeter. MCG as ammeter. So we have a moving coil galvanometer will be there. So to convert moving coil galvanometer into an ammeter, a resistance needs to be connected in parallel, and that resistance is called shunt resistance. Listen here. Before going to the diagram, I will say why we are connecting a parallel resistance in case of ammeter. Why we are not connecting series? See, ഈ galvanometer എന്ന് പറയുന്ന ഡിവൈസ് ഇത് ഭയങ്കര സെൻസിറ്റീവ് ആണ്. ഭയങ്കര സെൻസിറ്റീവ് എന്ന് പറഞ്ഞാൽ ലിസൺ ടു മീ, നോട്ട് ലിസൺ ടു ദി ബോർഡ്. ഓക്കെ, സോ ദിസ് ഈസ് വെരി സെൻസിറ്റീവ് ആണ്. ഈ galvanometer എന്ന് പറയുന്ന ഡിവൈസ് ഭയങ്കര സെൻസിറ്റീവ് ആണ്. അതിൻ്റെ യൂസ് എന്നാന്ന് കേട്ടാൽ ഇൻ ബേസിക്കലി ഇഫ് യു ആർ ഗിവിംഗ് എൻ 1 ampere ഓഫ് കറണ്ട് ഇൻ ടു ദാറ്റ് വൺ, ഓക്കെ, അതിൻ്റെ കപ്പാസിറ്റി, അതിന് മെഷർ ചെയ്യാൻ പറ്റുന്ന കപ്പാസിറ്റി എന്ന് പറയുന്നത് ഇറ്റ്സ് വെരി ലെസ്. സപ്പോസ് ഇഫ് ഐ വാണ്ട് ടു മെഷർ ലൈക്ക് 1 ampere കറണ്ട്, ഓക്കെ, മൈ galvanometer കപ്പാസിറ്റി ഈസ് 1 ampere. 1 ampere എന്ന് പറയുന്നത് 0 സ്റ്റാർട്ട് ചെയ്യും, അതിൻ്റെ റീഡിങ് 0.1, 0.2, അതിൻ്റെ മീറ്റർ സ്കെയിലാണ് പറയുന്നത്. Within the meter scale, 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, up to it's go to up to 1. So maximum full deflection is 1 ampere. Suppose I want to measure 2 ampere current. What we will do, because my equipment or my galvanometer maximum capacity is 1 ampere, but I want to measure more than 1 ampere current. Suppose I am giving a 2 ampere current. What will happen? The needle will go tuck and it will fall, will be here. Beyond that it cannot go. So it will, if you give a 2 ampere current also, if you give 100 ampere current also, the needle will always go to 1 ampere and stop it there, because the galvanometer meter scale capacity maximum 1 ampere. Beyond that it cannot go. So if I want to measure like a 2 ampere, 3 ampere, 4 ampere, 1000 ampere, what should I will do? To do that, what we will do means we will connect a parallel resistance. This resistance is called a shunt resistance, and its value is low comparable to the resistance of the galvanometer. The resistance of the galvanometer is Rg. This resistance is comparable to S in the value is very low comparable to that of Rg. See, I told my capacitance will be capacity of measuring the current will be 1 ampere, but I am giving 2 ampere. So if this galvanometer is, if this resistance is not there, what happens? The complete 2 ampere current will pass through the galvanometer. Galvanometer needle will go to one position. Beyond that it cannot measure. So now I am giving 2 ampere, that is beyond the limit of galvanometer. If a shunt resistance is connected in parallel and which has low value, what will happen? Suppose you assume, what will happen means you are giving like something like a 2 ampere current you are giving will be here. Out of this one, 0.5 ampere is going will be here. So what is balance will go here? 1.5 ampere will be here. Okay, so 1.5 ampere current is going and going out. This is what is happening. But in this case, practicality. So in practically, what is happening in that case? See, 0.5. 0.5. So I know this is if I am taking like x. So this is what? This is like 3x times, because idile x poida idu 0.5 nu sollum x, appo 1.5 nu sollum 3x, 3 times of 0.5 alle 1.5 nu sollum, so it become 3x. So this is x 0.5, so this become 1.5, so it become called 3x. Okay, so which means if a galvanometer the maximum reading 0 to 1 on, I told it's 1. Okay, so this case is applicable when a 1 ampere current is passing through this one. Now my current is coming like a 2 ampere. So what will happen? The galvanometer, the current passing through the galvanometer is now only 0.5. 0.5. So galvanometer will show to us, my current is 0.5 ampere. So 0.5 ampere is current flowing, but I know the ratio between 3x by x, 3x by x. This ratio I know because I know the value of shunt resistance. Because I know the value of shunt resistance, if this resistance is x, then this resistance should be x by 3. Then 3 times current will go higher in this one. So more current means less resistance. 3x current means x by 3 resistance. X current means 3x resistance. More resistance, less current. High current, less resistance. So I know this is 2 ampere I am giving, but if I am giving 2 ampere, my galvanometer is showing 0.5. Then immediately I know 2 ampere I am giving, my galvanometer is showing 0.5. I know 1.5 ampere is bypassed to somebody else. 1.5 ampere is bypassed to somebody else. I know these reasons, but I can measure the current. So if my reading is given as 0.5 meter, I know 1.5 ampere current extra coming to the galvanometer, then 1.5 plus 0.5 become 2. Galvanometer cannot hold it. So I have to bypass certain amount of current. So to bypass that, this bypassing pass we are giving through the low value of shunt resistance. Okay, but if it is 0.5, if the galvanometer reading is given as 0.5, that is inside the galvanometer. Now the whole system is connected to another meter scale, and that meter scale, what that meter scale will do, that meter scale will take this galvanometer value 0.5. Internally one circuit will be there, that circuit will calculate 0.5 plus, and this value will be there. What is this value? It is 1.5 ampere. So the internal circuit, electronic circuit will add, and this will give you a 2 ampere display to you outside. But internally, what is galvanometer? Galvanometer is only taking 0.5. So galvanometer will know 2 ampere is coming, 1.5 have taken, so 1.5 is going upward. So somehow we need to bypass the current, but still I need to give a correct value to the user who are using the ammeter equipment. So internal circuit will measure, okay, what is the rating of ammeter? 0.5. So balance 1.5 is going through that side. So 1.5 plus 0.5, I have to give a display to the user in the LCD panel. I have to give a user, okay, he is measuring 2 ampere is giving, he will getting 2 ampere. He is giving 5 ampere, he will get 5 ampere, like that. Now we know this ratio is 3x times. 3x times means if I am giving 15 ampere, current will be here. This is 3x times, this is x times, because 3 times it's higher. So how much current will be passing through this one? How much current? If I am giving 2 ampere, 0.5 is passing. So let me take it as maybe this is 16 venda, 4. Okay, 16 ampere current if I am giving. So how much current will be passing here? 4 ampere. How much current will pass will be here? 3 into 4. I know 12. So this 12 in the internal circuit, what will do? This 4 plus this 12 will add and give the user as 16 ampere experiences. So this is just for your understandability I am telling. So galvanometer cannot hold beyond certain limit of values. Galvanometer cannot hold. So if you want to measure beyond the limit of capacity of the galvanometer, what you need to do? You need to bypass the extra amount of current. That value you should know. So how we are bypassing using the low value of shunt resistance. Now we know based on the concept of voltage, we know in parallel circuit, voltage is same. Parallel circuit voltage same market. So two parallel circuit, this is one circuit and this is another circuit. So voltage means what? Current into resistance. I minus Ig into S is equal to Ig into G. I minus Ig into S is equal to Ig into G. Okay, here the value of the shunt resistance is Ig into G. Ig is the galvanometer passing, I is the total current, so I minus Ig. Okay, so in parallel circuit, so what we have saying, so to convert moving coil galvanometer into ammeter, into a meter. A low value of shunt means parallel. Shunt എന്ന വേർഡിൻ്റെ മീനിങ് പാരലൽ ആണ്. A low value of shunt resistance needs to be connected in parallel. Needs to be connected in parallel. Important, not in series. In parallel. Low value of shunt resistance needs to be connected in parallel. Okay. So hope all this information is very clear with you. I have done with the chapter moving charges and magnetism. Okay, the chapter is over. As usual, I am doing for other chapters also. We have certain set of questions with me, and we'll see the questions here. In the next sessions, we'll see the question discussions part. Okay, hope the theory session is understandable to you. Go through the complete notebook, and by doing the question also you will become strong in that area. So try to practice as much as questions you can. Okay, so thanks a lot for watching this video, and have a nice day.